Hello, in this lecture we'll find out the area of the orange shape using two different methods. In the drawing we have square ABCD. You know that one side of square ABCD equals to 10 units. Inside square ABCD we have two semicircles, semicircle APD and semicircle CPD. They intersect with each other and create the blue lens. We also have quarter circle AQBD. This quarter circle intersects with this semicircle and create the big lens. And our mission is to find out the area of this orange shape. Okay, so in order to find out the area of this orange shape, we will actually, it is very easy to see from the drawing that the area of the big lens minus the area of the blue lens equals to the area of the orange shape. So write it down. So the area of this orange shape equals to the area of the big lens minus the area of the blue lens. I'll repeat again. The area of the orange shape equals to the area of the big lens minus the area of the blue lens. Okay, so in order to find out the area of the orange shape, we will use two methods. In the first method, we will develop a formula for the area of any lens, and then we'll use the formula that we will develop in order to find out the area of the big lens. We'll use the same formula in order to find out the area of the blue lens. We'll subtract the two areas from each other, and this will give us the area of this orange shape. In the second method, we will directly find out the area of the blue lens, and then we directly find out the area of the big lens. We'll subtract the two areas from each other, and it will give us the area of this. This will be equal to the area of this orange shape. Okay, so before we start to answer the question, I will clarify two concepts. The first concept is the area of a sector. If the area of this green sector, it is equal to the angle between the legs of the sector, that is theta, over 360 degrees, or in terms of radians is 2 pi. 2 pi radians is 360 degrees. So the ratio between the two angles, that is theta over 2 pi, will give us the percent of the amount of percentage that this sector occupies out of the area of the whole circle, and then when we will multiply that percentage by the area of the circle, it will give us exactly the area of this circle. So theta over 2 pi is the ratio between the two angles times the area of the circle, that is pi r square, will give us exactly the area of this sector. And the second concept that I will clarify is the area of this circular segment AB. The area of this circular segment AB will be equal to the area of sector AOB minus the area of triangle AOB. Again, the area of sector AOB minus the area of triangle AOB will give us exactly the area of this circular segment AB. Okay, so we'll start with the first method, and here we have two semicircles that intersect with each other, and they create this length. The length is the common area that was created by the intersection of those two semicircles with each other. And our mission is to find out the area of this length, and then we use the formula in order to find out the area of this blue length. Then we find out the area of the big length, and we will subtract the areas from each other, and this will be equal to the area of this orange shape. Okay, so let's start. So those two semicircles have different radii. Here we define the center of this semicircle as O. This point is point L, this point is point M. Okay, so point O is the center of the semicircle. Point M is the point on the semicircle itself, that is to say, line segment MO is the radius of this semicircle. So we will define the radius of this semicircle as A, that is to say, the radius of this semicircle equals to A units in its length. Here, point N is the center of this semicircle. Point M is a point on the semicircle itself, on this semicircle itself, that is to say, line segment NM is the radius of this semicircle. We define the radius of this semicircle as B. Here, point N is the center of this semicircle. Point L is the point on this semicircle itself. Therefore, NL is also the radius of this semicircle, that is equal to B units according to our definition. Again, here point L is a point on this semicircle itself. Point O is the center of this semicircle, that is to say, LO is the radius of this semicircle, that is equal to A units according to our definition. So here we have here the radius NB of this semicircle. It is tangent to this semicircle at point M. Point M is the point of tendency. Okay, so point M is the point of tendency of tangent NC with this semicircle. And we have here the radius OM that is drawn to the point of tendency, that is to say, it is drawn to point M, that is the point of tendency, of tangent NC with this semicircle, and whenever we have a radius that is drawn to the point of tendency, then tangent NM will be perpendicular to the radius MO. So if NM is perpendicular to NO, it means that this angle equals to 90 degrees. Likewise, we have here the radius LO that is drawn to the point of tendency. Here L is the point of tendency. Of tangent NL with this semicircle. And we have the radius NL that is drawn to the point of tendency, that is to say it is drawn to point L, that is the point of tendency of tangent NL with this semicircle. And whenever we have a radius that is drawn to the point of tendency, then tangent NL will be perpendicular to the radius OL. So if NL is perpendicular to OL, it means that this angle equals to 90 degrees. Okay. In the next step, we'll join points M and L together by a straight line. We join points N and O together by a straight line. So I repeat again that our mission is to find out the area of this lens that was created by the intersection of those two semicircles with each other. Okay. So I write here that our mission is to find the area of this lens, of the lens so our mission is to find out the area of the lens this lens, and because of the fact that this lens was created by the intersection of two semicircles that have different radii A and B, so this lens could be any lens. Okay, so we will use the general formula that we will find for the area of a lens in order to find out the area of the blue lens. Then we will use the same formula in order to find out the area of the big lens, and then we will subtract the two areas from each other, and this will give us the area of this orange shape. I will repeat again that a lens is the current area that was created by the intersection of those two semicircles with each other. Okay, and because of the fact that the area, that the radii of the two semicircles are not equal to each other, they are not specific radii, you can use this formula in order to find out the area of any lens. And we use the formula that we will find in order to find out the area of this lens, and in order the blue lens, and in order to find out the area of this big lens. Okay, then we'll subtract the areas from each other, and we'll get the area of this orange shape that we are looking for. This will be the first method. While in the second method, we will directly find out the area of the blue lens, we directly find out the area of the big lens, and we will subtract the areas from each other, and this will give us the area of this oval shape. Okay, so we continue in the first method. In the first method, we are looking for a formula of this lens that could be any lens. So, in the first step, we'll find out the area here. The straight line ML divides this lens into two parts. Therefore, we will find out the area of each part. Then we will add the areas together, and this will be the area of this lens that could be any lens. Okay. So here, we have circular segment ML. The upper circular segment ML. So what is the area of the upper circular segment ML? The area of the upper circular segment ML, the green shape ML, so the area of this upper circular segment ML will be equal to the area of sector MOL So this is sector MOL, and from the area of sector MOL, we'll subtract the area of this triangle MOL, and this will give us the area of the upper circular segment ML. So this is triangle MOL. We subtract the area of triangle MOL from the area of sector MOL, and this will give us the area of the upper circular segment ML. Okay. So, in order to find out the area of sector MOL, we have to find out angle, the size of angle MOL, the size of this angle, that is the angle between the legs of sector MOL. Okay. So here we define angle MON as theta. Those two triangles can go into each other according to side rule. Here I'll explain it. Side MO equals to side OL. They are both equal to 8, so they are equal to each other. Side MN equals to side NL. So Why? Because they are both equal to B, because therefore they are equal to each other. And finally, NO is the common side that belongs to both triangles, therefore this side equals to itself. In conclusion, those two triangles can go into each other according to side rule. And from the fact that the two triangles can go into each other, we will conclude that those two angles are equal to each other. Those two angles are equal to each other according to the rule that corresponding angles that can go in triangles are equal to each other. Okay? But according to our definition, this angle equals to theta. Therefore, this angle must be also equal to theta because of the fact that those two angles are equal to each other. So in conclusion, we found out that the size of angle MOL is theta plus theta, that is 2 theta. So the size of this angle MOL equals to 2 theta. So, yeah. Okay, so what is the area of sector MOL? The area of sector MOL equals to 2 theta over 2 pi. The ratio between those two angles will give us the relative percentage that this sector MOL occupy out of the whole circle, and when we will multiply the relative percentage by the area of the whole circle, that is equal to pi r squared, and r equals to a, so it is pi a squared. This will give us the area of this sector MOL. I'll remind you that 2 pi radians is equal to 360 degrees in terms of degrees. 2 pi radians is 360 degrees, that is the full angle of the whole circle. Whole circle, actually, if the angle, the size of the angle that is the whole circle is 360 degrees or 2 pi radians. Here, if we have a circle, the angle that this circle actually creates is 360 degrees. Okay? Or 2 pi radians in terms of radians. So here we have pi in the numerator and pi in the denominator, so pi will get cancelled. We have 2 in the numerator and 2 in the denominator, so 2 also will get cancelled. So in conclusion, the area of sector MOL equals to theta times here r equals to a. R equals to a is the radius of this circle, therefore it is theta. R is a, so it is theta times a squared. That is the area of sector MOL. We will not calculate the area of this triangle. We'll do it later. The next step, we'll find out the area of the lower circular segment of this length, that could be any length. We'll find out the area of this orange shape that is defined as the lower circular segment of this lens that could be any lens. So the area of the lower circular segment ML of the lens that could be any lens it will be equal to the area of sector L and M this is sector M and L minus the area of triangle M and L minus the area of triangle M and L. It's very easy to see from the drawing that if you subtract the area of triangle M and L from the area of sector M and L, you will get exactly the area of this lower circular segment ML. This is the lower circular segment ML. Okay. In order to find out the area of sector M and L, we have to find out the area of this angle. Okay. So we have to find out the size of angle M and L, that is the angle, the size of the angle between the legs of sector M and L. We'll focus on this right triangle OMN. This angle equals to theta. This angle equals to 90 degrees or pi over 2 in terms of radians. So this angle must be equal to pi over 2 minus theta, or 90 degrees minus theta in terms of degrees. Likewise, if we focus on this right triangle, this angle equals to theta. This angle equals to 90 degrees, therefore this angle must be equal to pi over 2 minus theta in terms of radians. Now we will add together the two angles, and this will give us the size of angle M and L. So the size of angle M and L, that is actually this angle, it will be equal to pi over 2 minus theta plus pi over 2 minus theta. So here pi over 2 plus pi over 2 is pi, and minus theta plus minus theta is minus 2 theta. So in conclusion, we found out that the size of this angle M and L, equals to pi minus 2 theta. Pi minus 2 theta radians, of course. So here we can write down that this angle equals to pi minus 2 theta radians. Now it is very easy to find out the area of sector M and L. the area of sector M and L will be equal to the ratio between the angle that is between his legs, that is pi minus 2 theta, over the size of the angle of the whole circle, that is 360 degrees, or 2 pi radians in terms of radians. This ratio will give us the relative percentage of the out of the area of the whole circle that this sector occupies, and we will multiply the percentage by the area of the whole circle, that is actually equals to here pi r square, but here r equals to b, therefore it is pi b square. This will give us exactly the area of sector M and L. Here we have pi in the numerator and pi in the denominator, so pi will get cancelled. We'll open the brackets here and we get that here pi times b square over 2 minus 2 theta times b square over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So in conclusion, the area of sector M and L equals to pi b square over 2 minus theta times b square. Okay? And we have to subtract also the area from the area of the sector, the area of triangle M and L. So here, so we will do it in the next step. And finally, the sum of the two areas, that is to say, the area of the upper circular segment plus the area of the lower circular segment, will give us the area of this length, that could be any length. Okay? So, here, the area of the length, that could be any length, will be equal to the area of the upper circular segment. This is the upper circular segment plus the area of the lower circular segment. You've already found out that the area of the upper circular segment equals to the area of sector MOL plus the area of triangle MOL This is the area of the upper circular segment minus the area of triangle MOL, of course, while the area of the lower circular segment, the shape in the orange color, is equal to the area of sector M and L. This is sector M and L. That's the area of triangle M and L. Okay. And we have already found out that the area of those two sectors, the sum of the areas of those two sectors, is actually equals to the area of this sector is equal to theta times a squared, while the area of this sector it is equal to, so it is plus the area of sector M and L, that is equal to pi b squared over 2, pi b squared over 2 minus theta b squared is the area of this sector. Now we have to subtract the sum of the areas of the two triangles from this sum. Here we have to subtract the areas of those two triangles. From the area, from the sum of the areas of the two sectors. Okay? In order to find out the areas of the two triangles, we'll combine them together. This way we create a quadrilateral So this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we will join points O and N together by a straight line. By joining points O and N together by a straight line, we created here two right triangles. The green right triangle, triangle MON, and the orange right triangle, triangle NOL. So you know that OL equals to A units and L equals to B units. while MO equals to A units and MN equals to B units. So the area of the green right triangle AB equals to the base of the triangle that is B times the height to the base that is A over 2. So it is B times A over 2 plus the area of the orange right triangle OLN. It is equal to the base of the triangle that is A times the height to the base that is B over 2. So here we found out that the sum of the areas of the two triangles equals to BA over 2 plus AB over 2. BA plus AB is BA plus BA, that is 2AB over 2. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So in conclusion, we found out that the sum of the areas of those two triangles is A times B. So we have to subtract from the sum of the areas of the two sectors AB. And this will give us the area of this length that could be any length. So now we can write down that the area of the length that could be any length so the area of this length it is equal to the area of sector MOL, that is theta A square, plus the area of sector MNL, that is equal to pi B square over 2 minus theta B square minus the sum of the areas of the two triangles that we have already found out that is equal to AB, so minus AB. So this is actually the area of the length that could be any length. Here we'll take theta as a common factor out of these two expressions, and we'll get that the area of this length that would be any length is equal to, here we took theta as a common factor, so what is left from this expression after we took from it theta as a common factor? What is left? This is actually A square. And what is left from this expression after we took from it theta as a common factor? What is left is actually minus B square. And we have to add also pi B square over 2 minus AB. So this is the general formula for the area of any length. Okay? In the next step we will find out the value of theta itself, because we actually want to create a formula that the only missing variables that the formula for the area of a length will have, they will be only A and B that are the radii of the two shapes that intersect with each other. Okay, so here, so I'll copy the right triangle MON in this page, and we will derive from it the value of angle theta. So this is right triangle MON. This angle equals to 90 degrees. This angle equals to theta. Side MO equals to A. Side MN equals to B. So in the right triangle, triangle MNO, it is very easy to see that tangent theta equals to MN over MO. Okay? Here MN equals to B and MO equals to A, so in conclusion we found out that tangent theta equals to B over A, but we are looking for theta itself. In order to find out the value of theta itself, we will operate the opposite function of tangents, that is tangents minus 1 on the result, that is B over A, and this will give us the value of theta itself. So theta will be equal to tangents minus 1. We will operate the opposite function of tangents, that is tangents minus 1 on the result, that is B over A, and this will give us the value of theta itself. So in conclusion, theta equals to tangents minus 1, that is the opposite function of tangents. We operate the opposite function of tangents on B over A, and this equals to theta. In the next step, we'll substitute theta by tangents minus 1 of B over A. And you will get that the area of the lens, that could be any lens, will be equal to theta. We already found out that theta equals to tangents minus 1 of B over A times A square minus B square plus pi B square over 2 minus AB. We actually found out a formula for the area of any lens. Therefore, we can use this formula in order to find out the area of the big lens, and also in order to find out the area of this blue lens. Okay, so first of all we will find out the area of the big lens. We find out the area of this big lens. It's very easy to see from the drawing that the big lens, this big lens was created by the intersection of the quarter circle, this quarter circle, with the semicircle. The intersection of the quarter circle with this semicircle created the blue lens. For that reason, the radius of the quarter circle will be equal to A, and the radius of the semicircle will be equal to B. So A equals to the radius of the quarter circle, and it is very easy to see from the drawing that the radius of this quarter circle equals to 10 units. So A equals to 10 units. What is the radius of this semicircle? It is very easy to see that the diameter of this semicircle equals to 10. Therefore, the radius will be equal to 5. So B equals to 5. In conclusion, we found out that A equals to 10, B equals to 5. Now we can put the values of A and B inside the formula for the area of the lens, and this will give us the area of this big lens. So the area of the big lens will be equal to tangent minus 1 of B over A, but here B equals to 10, so we'll substitute B by 10, and substitute here it is actually A equals to 10 and B equals to 5. So here we have B, so B equals to 5. So here we have 5 over A, here A equals to 10. So it is 5 over 10. It is 5 over 10. So here, so I will write down the formula again. So the area of the big lens equals to tangent minus 1 of B over A. B is 5, A is 10, so 5 over 10 is 1/2, and 1/2 is 0.5. So it is tangent minus 1 of 0.5. Here A equals to 10, so A square is 10 square minus B square. B equals to 5, so B square is 5 square plus pi times B square. B is 5, so it is 5 square. B square is 5 square over 2 minus A times B. A is 10 and B is 5, so it is minus 10 times 5. So here we found out that the area of the big lens equals to 10 square is 100 minus 5 square. 5 square is 25. 100 minus 25 is 75. So this expression will be equal to in total to 75 times tangent minus 1 of 0.5 plus pi 5 square over 2. 5 square is 25. 25 over 2 is 12.5. So in total this expression equals to 12.5 pi. minus 10 times 5, 10 times 5 is 50, so it is minus 50. So in conclusion, we found out that the area of the big lens equals to 75 times tangents minus 1 of 0.5 plus 12.5 pi minus 50. In the next step, we'll find out the area of the blue lens, of this blue lens. It's very easy to see from the drawing that the blue lens was created by the intersection of two semicircles, and we know that the radius of each semicircle equals to 5 units. So here we'll get that A equals to B equals to 5 units. A equals to 5 units and B also equals to 5 units. Now we'll put the values of A and B inside this formula and we'll get the area of the blue lens. So the area of the blue lens of this blue lens will be equal to tangents minus 1 of B over A. B is 5, A is 5, so 5 over 5 is 1 times A squared. A is 5, so A squared is 5 squared minus B squared. B is 5, so B squared is 5 squared. Five squared minus 5 squared is 0, so this expression will be equal to 0, of course, plus pi B squared. B is 5, so B squared is 5 squared, that is 25, so it is 25 times pi over 2 minus AB. A is 5, B is 5, so 5 times 5 is 25. In conclusion, we found out that the area of the blue lens equals to, this expression equals to 0, so we have here 25 over 5 is 12.5, so in total this expression equals to 12.5 pi minus 25. This is the area of the blue lens. Okay. And we know that the area of this orange shape equals to the area of the big lens minus the area of the blue lens. So I write it down. The area of the orange shape that we are looking for in this lecture is equal to the area of the big lens minus the area of the blue lens. Okay, So the area of the orange shape will be equal to the area of the big lens. We have already found out that the area of the big lens equals to 75 times tangents minus 1 of 0.5 plus 12.5 pi minus 50. So this is the area of the big lens minus the area of the blue lens. And we already found out that the area of the blue lens equals to 12.5 pi minus 25. Now we will open the brackets here and we will get that the area of the orange shape equals to 75 times tangents minus 1 of 0.5 plus 12.5 pi minus 50. We'll open the brackets here. So here we get minus 12.5 pi, and here we have minus, and minus is plus, so minus 25 is plus 25. So here we have 12.5 pi minus 12.5 pi is 0, so those two expressions will get cancelled. And here minus 50 plus 25 is minus 25. So in conclusion, we found out that the area of the orange shape equals to 75 times tangents minus 1 of 0.5 minus 25. And the value of tangents minus 1 of 0.5, it is equal to 0.46. So we'll substitute tangents minus 1 of 0.5 by 0.46 and we get that the area of the orange shape equals to 75 times 0.46 minus 25. Here 75 times 0.46 is 34.77, and we have to subtract here minus 25. And 34 minus 34.77 minus 25 equals to 9.77 square units. And this is the area of the orange shape. The area of the orange shape equals to 9.77 square units. I'll repeat again that the area of this orange shape DPQ equals to 9.77 square units. We finished with the first method. In the next step I will present to you the second method. as I've already mentioned, in the second method, we will directly find out the area of the big lens, then we'll find out directly the area of this blue lens, and we'll subtract the two areas from each other, and this will give us the area of this orange shape. We will not use any formula, any general formula for the area of a lens, but we will directly calculate the area of the blue lens, then we will calculate the area of the big lens, we'll subtract the two areas from each other, and this will give us the area of this shape, the orange shape. So we start. First of all, we'll find out the area of the blue shape. So our mission in the first step is to find out the area of this blue shape, and so I'll write it down. So our mission is to find out the area of the blue lens. It is very easy to see from the drawing that the blue lens was created by the intersection of the two semicircles with each other. Okay? And we have already found out that the radius of each semicircle is equal to 5 units. Actually, we can use the drawing from the first method here. We'll use the drawing from the first method, and we know that in our case the radius of both semicircles it is equal to 5 units, so here A will be equal to B will be equal to 5 units. Okay, so we can use the same drawing here. This is also the intersection of the two semicircles with each other that created this lens. And we know that the radius of each lens is 5 units, so here A will be equal to 5 and B will be equal to 5 also. I repeat again that the radius of each semicircle is equal to 5 units, so here is 5, this is equal to 5 units, and also equals to 5, and L equals to 5. So here we divided the blue lens into two parts. And because of the fact that the radius of each semicircle is equal to 5 units, it means that the lower circular segment will be with the same area of the upper circular segment. Therefore, we will multiply the area of the upper circular segment by 2, and this will give us the area of the blue lens. Okay, our mission is to find out the area of the blue lens. find it directly and not by using any formula. Okay. So what is the area of this circular segment ML? The area of circular segment ML the area of this circular segment ML, according to the formula that I presented to you in the beginning of the lecture, it will be equal to the area of sector MOL So this is sector MOL minus the area of triangle MOL. It's very easy to see from the drawing that if we subtract the area of triangle MOL from the area of sector MOL, we'll get exactly the area of circular segment, this circular segment, segment ML. Okay? But here, sector MOL, it is a quarter circle, because this angle equals to 90 degrees. And we know that the area of any quarter circle equals to the area of the circle over 4. That is to say, the area of this quarter circle MOL will be equal to the area of the circle that is pi r squared, and r equals to 5, so it is pi 5 squared over 4. So this is the area of sector MOL minus the area of triangle MOL. The area of triangle MOL equals to the base of the triangle that is 5 times the height to the base that is also 5 over 2. So here we actually found out the area of the circular segment ML. Now we will multiply this area by 2 and we will get the area of the blue shape. So the area of the blue shape the blue lens, of course. So the area of the blue lens will be equal to 2 times the area of sector ML, and the area of sector ML is this expression, so it is 2 times the area of circular segment ML. 5 squared is 25, so it is 25 pi over 4 minus 5 times 5 is 25 over 2. Okay. So here we'll open the brackets and we'll get that 2 times 25 pi over 4 equals to 25 times 2 over 2 . So here we divide both the numerator and the denominator by 2. So here 2 over 2 is 1, so in the numerator we're left only with 25 pi over 4 over 2 is 2. And here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled and we're left only with 25. And 25 over 2 is 12.5 pi, is 12.5. So we found out that the area of the blue lens, in conclusion, it is equal to 25 over 2 is 12.5 pi. So this expression in total equals to 12.5 pi minus 25. I'll repeat again that we found out that the area of the blue lens equals to 12.5 pi minus 25 square units. We finished with the first step. In the second step, we will find out the area of the big lens. It is very easy to see from the drawing that this big lens was created by the intersection of the quarter circle with this semicircle. Okay, again, this big lens was created by the intersection of the quarter circle with this semicircle. Okay. Okay, so we want to find out the area of this big lens. Well, write it down that our mission is to find out the area of the big lens. That is to say, to find out the area of this shape that is the big lens. This is the radius of the quarter circle that is equal to 10 units. Here point O is the center of the quarter circle. Point L is the point on the quarter circle itself. That is to say, OL is the radius of this quarter circle that is equal to 10 units. Here, point M is the center of this semicircle. Point L is a point on the semicircle itself. That is to say, ML is the radius of this semicircle, that is equal to 5 units. In the next step, we join the two centers together, the center of the semicircle with the center of the quarter circle. Here point M is the center of the semicircle, point N is a point on the semicircle itself, therefore Mn is the radius of this semicircle, that is equal to 5 units. Okay? Actually, point N is the point of tendency of tangent Mn with this quarter circle. Okay, point N is the point of tendency of tangent Mn with this quarter circle. So we have here the radius On of the quarter circle that is drawn to the point of tendency. That is to say, it is drawn to point N, that is the point of tendency of tangent Mn with this quarter circle. Whenever you have a radius that is drawn to the point of tendency, then tangent Mn will be perpendicular to the radius NO. So if Mn is perpendicular to NO, it means that this angle equals to 90 degrees. And here also the radius ML is tangent to the semicircle at point L. So L is the point of tangency of tangent ML with this quarter circle. And we have here the radius OL of the quarter circle that is drawn to the point of tendency. That is to say, it is drawn to point L, that is the point of tendency of tangent ML with this quarter circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ML will be perpendicular to the radius LO. So if ML is perpendicular to LO, it means that this angle also equals to 90 degrees. Okay, this is actually according to rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the next step, we join points N and L together by a straight line. By joining points N and L together by a straight line, we actually divided the big length into two parts. So we calculate the area of each part, we'll add the two areas together, and this will be the area of the big length. We'll start with the upper part, upper circular segment of the big length, and we'll find out the area of the upper circular segment of this big length. We define angle MON as theta. Those two triangles can go into each other according to angle, according to side rule. I'll explain why they can go into each other. First of all, those two sides are both equal to 10 units, therefore they are equal to each other. Those two sides they are both equal to 5 units, therefore they are equal to each other. And finally, side OM is a common side that belongs to both triangles, so this side equals to itself. So we actually found out that those two triangles, triangle ONM and triangle OML, can go into each other according to side rule. From the fact that the two triangles can go into each other, we conclude that those two angles are equal to each other according to the rule that corresponding angles and congruent triangles are equal to each other. Okay? So those two angles are equal to each other. So if this angle equals to theta, then this angle must be also equal to theta because of the fact that those two angles are equal to each other. So we actually found out that angle NOL equals to 2 theta. Theta plus theta is 2 theta. So what is the area of the upper circular segment NL? The area of the upper circular segment NL, the green shape, the area of the upper circular segment NL, it will be equal to the area of sector NOL minus the area of triangle NOL. I repeat again. The area of circular segment NL will be equal to the area of sector NOL minus the area of triangle NOL. It is very easy to see from the drawing that if you subtract the area of triangle NOL from the area of sector NOL, you will get exactly the area of circular segment NL. And we know that the angle between the legs of sector NOL is equal to 2 theta. Therefore, the area of this sector NOL will be equal to 2 theta over 2 pi. That will give us the relative percentage that this sector occupies out of the area of the whole circle. And when we multiply the relative percentage by the area of the whole circle, that is pi r square, and here r equals to 10, so it is pi 10 square, it will give us exactly the area of sector NOL. So here we have pi in the numerator and pi in the denominator, so pi will get cancelled. We have 2 in the numerator and 2 in the denominator, so 2 also will get cancelled. So in conclusion, the area of sector NOL equals to 10 square is 100, So it is 100 times theta, or 100 theta, minus the area of triangle NOL. So the area of triangle NON equals to the multiplication of the two sides by each other, that is 10 times 10 times sinus the angle between the two sides, that is sinus 2 theta over 2. In conclusion, we found out that the area of the upper circular segment NL it is equal to 100 times theta minus 10 times 10 is 100, and 100 over 2 is 50. So it is minus 50 times sinus 2 theta. Okay? In the next step, we find out the value of theta and the value of sinus 2 theta, and we substitute theta and sinus theta 2 theta in this expression by the values that we will find out for them. Okay? So in order to find out the values of theta and sinus 2 theta, I will draw the right triangle triangle NOL. This new present will derive the values of theta and sinus theta from the right triangle NOL. So this is the right triangle NOL. It consists angle theta, of course. That is the reason that we choose the right triangle NMO. So in the right triangle NMO, it is very easy to see that tangent theta here is equals to 5, this equals to 10. It is very easy to see that tangent theta equals to NM over NO. NM equals to 5, NO equals to 10. 5 over 10 is 1/2, that is 0.5. So in conclusion, I found out that tangent theta equals to 0.5. Now we want to find out the value of theta itself. In order to find out the value of theta itself, we will operate the opposite function of tangents on the result, and this will give us the value of theta. So theta equals to the opposite function of tangents is tangents minus 1 of 0.5. And this equals to theta. So we found out in conclusion that theta equals to tangents minus 1 of 0.5. I repeat again that tangents minus 1 is the opposite function of tangents. In the next step, we will find out the value of sinus 2 theta. So I'll copy again the right triangle NOM here. we'll implement the Pythagoras theorem on the right triangle NOM in order to find out the hypotenuse OM. Okay, so in the right triangle NOM, by PT is abbreviation for Pythagoras theorem, we'll get that OM squared, the square of the hypotenuse, equals to the sum of the squares of the perpendiculars. That is to say, it is equals to ON squared. ON is 10, so ON squared is 10 squared, that is 100, plus NM squared. NM is 5, so NM squared is 5 squared, that is 25. 100 plus 25 is 125. We take out of this equation and we get that OM equals to the square root of 125. 125 is 25 times 5, so we substitute 125 by 25 times 5. We take out of this equation and we get that the square root of 25 is 5. Inside the root we left only with 5. So in conclusion, we found out that the hypotenuse OM of the right triangle NOM equals to 5 times square root of 5. Now our mission is to find out the value of sinus 2 theta, and we have the trigonometric identity that sinus 2 theta equals to 2 sine theta cosine theta. So here sinus 2 theta equals to 2 times sinus theta. From this triangle you can derive the value of sinus 2 theta. Here it is very easy to see that in this right triangle NOM, sinus theta equals to NM over OM. NM is 5, OM is 5 times square root of 5, so in conclusion we found out that sinus theta equals to 5 over 5 times square root of 5. And we have to multiply it by cosine theta. What is the value of cosine theta? It is very easy to see from the triangle NOM that cosine theta equals to NO over OM. NO is 10 and OM is 5 times square root of 5. So in conclusion we found out that cosine theta equals to 10 over 5 times square root of 5. So we found out the value of sinus 2 theta. Here we have 5 in the numerator and 5 in the denominator, so 5 will get cancelled. So in the numerator we have here 10 times 2. In the denominator we have square root of 5 times square root of 5 is 5 times 5. Here 10 over 5 is 2. So in the numerator we have 2 times 2, that is 4. In the denominator we left only with 5. So in conclusion, we found out that sinus 2 theta equals to 4/5. Okay, sinus 2 theta equals to 4/5. So I will write down the things that we found out here. Again, here in the new page, we have already found out that tangents minus 1 of 0.5 is equal to theta. This is the value of theta according to what we have already found out. And we have already found out that the value of sinus 2 theta is 4/5. Okay? And I also found out that the area of the upper circular segment of the big length NL, it is equal to (100 times theta minus 50 times sinus 2 theta. Now we'll substitute theta by tangent minus 1 over 0.5, and we'll substitute sinus 2 theta by 4/5. And we'll get that the area of circular segment NL equals to 100 times, and theta is tangent minus 1 of 0.5, minus 50 times sinus 2 theta, and we've already found out that sinus 2 theta equals to 4/5. So we substitute sinus 2 theta by 4/5, and we'll get that the area of the upper circular segment NL is equals to 100 times tangent minus 1 of 0.5. Here 50 over 5 is 10, and 10 over 4 is 40. So here, in total, this expression equals to minus 40. Okay, so in conclusion, we found out that the area of the upper circular segment NL equals to 100 times tangent minus 1 over 0.5 minus 40. In the next step, we find out the area of the lower circular segment. We found out the area of this lower circular segment NL, and we will add the two areas together, and this will give us the area of the big lens. And then we'll subtract the two areas from each other. We'll subtract the area of the blue lens, we'll subtract the area of the blue lens from the area of the big lens, and this will give us the area of the orange shape. So our mission is here is to find out the area of the big lens, but here we are looking for the lower circular segment of the big lens. Okay, this is our mission, to find out the area of the lower circular segment of the big lens. Here we have already found out that we have here this angle equals to 90 degrees. I repeat again that our mission here is to find out the area of the lower circular segment of the big lens. To find out the area in the green shape. On this green shape, the lower circular segment. So we'll focus on the right triangle ONM. In the right triangle ONM, this angle equals to theta, this angle equals to 90 degrees, that is pi over 2 in terms of radians. So this angle must be equal to pi over 2 minus theta. The same thing is true in the right triangle OLM. This angle equals to theta, this angle equals to 90 degrees, so this angle must be equal to pi over 2 minus theta. We will add the two angles together, and this way we will find out the size of angle NML. Okay, so here pi over 2 minus theta plus pi over 2 minus theta equals to pi over 2 plus pi over 2 is pi, minus theta plus minus theta is minus 2 theta. So in conclusion, we found out that the size of this angle NML, the size of this angle, it is actually equals to pi minus 2 theta. Okay. Now we'll find out the area of the lower circular segment NL. So what is the area of the lower circular segment NL? The area of the lower circular segment NL is equal to the area of sector NML minus the area of triangle NML. Again, the area of circular segment NL equals to the area of sector NML minus the area of triangle NML. So write it down. Is equal to the area of sector NML I repeat again, the area of the lower circular segment NL is equal to the area of sector NML minus the area of triangle NML. Okay? And the area of sector NML equals to the angle between its legs is pi minus 2 theta over 2 pi times the area of the circle, that is pi r squared, and r equals to 5, so pi r squared is pi times 5 squared. We have pi in the numerator and pi in the denominator, so pi will get cancelled. So the area of sector NML, we'll open the brackets here and we'll get that it is pi times 5 squared is 25 over 2 minus 2 theta times 25 over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So here I found out that the area of sector NML equals to 12 over 2 is 25 over 2 is 12.5. So this expression in total equals to 12.5 pi minus 25 theta. 25 times theta. This is the area of sector NML, and we have to subtract from it the area of triangle NML. And the area of triangle NML equals to the multiplication of the two sides together, that is 5 times 5 is 25, times sinus, the angle between the legs is sinus pi minus 2 theta over 2. So in conclusion, we found out that the area of the lower circular segment NL equals to 12.5 pi minus 25 theta. Here we have minus 25 over 2, and sinus pi minus 2 theta equals to sinus 2 theta. And we already found out that sinus 2 theta equals to 4/5, so we'll substitute sinus 2 theta by 4/5, and we'll substitute theta by tangents minus 1 of 0.5. So in conclusion, we found out that the area of the lower circular segment NL of the big lens equals to 12.5 pi minus 25 theta, but we already found out that theta equals to tangents minus 1 of 0.5, so we substitute theta by the tangents minus 1 of 0.5 minus 25 over 2, and sinus 2 theta is 4/5. So we substitute sinus 2 theta by 4/5. So here we have 25 over 5 is 5. 5 times 4 is 20, and 20 over 2 is 10. So in conclusion, we found out that the area of the lower circular segment NL, it is equal to 12.5 pi minus 25 times tangents minus 1 of 0.5 minus 10. Okay. Now we will add the upper circular segment to the lower circular segment. It will give us the area of the big lens. The area of the big lens equals to the area of the upper circular segment plus the area of the lower circular segment. Okay. So I'll write it down that the area of the big lens equals to the area of the upper circular segment NL plus the area of the lower circular segment NL. Okay. So the area of the big lens equals to the area of the upper circular segment equals to 100 times tangents minus 1 of 0.5 minus 40 plus the area of the lower circular segment, that is equal to 12.5 pi minus 25 tangents minus 1 of 0.5 minus 10. So in conclusion, the area of the big lens equals to 100 tangents minus 1 of 0.5 minus 25 tangents minus 1 of 0.5 equals to 75 times tangents minus 1 of 0.5. And we have here minus 40 minus 10 is minus 50 plus 12.5 pi square units. This is actually the area of the big lens. We have already found out that the area of the blue lens equals to 12.5 pi minus 25, so the area of the big lens minus the area of the blue lens is the area of the orange shape that we are looking for in this lecture. Okay, so here the area of the orange shape equals to the area of the big lens minus the area of the blue lens. Okay, so the area of the orange shape equals to the area of the big lens, and we already found out that the area of the big lens equals to 75 times tangents minus 1 of 0.5 minus 50 plus 12.5 pi. And we have to subtract from the area of the big lens the area of the blue lens, and the area of the blue lens equals to 12.5 pi minus 25. Here we will open the brackets and we'll get that the area of the orange shape equals to 75 times tangents minus 1 of 0.5 minus 50 plus 12.5 pi. Here we will open the brackets and we get that this equals to minus 12.5 pi. Here we have minus and minus is plus, so it is minus 25, it is plus 25. So here 12.5 pi minus 12.5 pi is 0. So those two expressions will get cancelled. And we have here minus 50 plus 25 is minus 25. So in conclusion, we found out that the area of the orange shape equals to 75 times tangents minus 1 of 0.5 minus 25. And we know that tangents minus 1 of 0.5, it is equals to 0.46. Now we'll substitute tangents minus 1 of 0.5 by 0.46, and we get that 75 tangents minus 1 of 0.5 equals to 0.46. So we multiply it by 0.46 minus 25. 75 times 0.46 is 34.77 minus 25. So 34.77 minus 25 equals to 9.77. So we found out that the area of the orange shape equals to 9.77 square units. Okay, the area of this orange shape equals to 9.77 square units. In the next step, we will summarize the lecture. So actually, we found out the area of this orange shape in two different methods. In the first method, we found out a general formula for the area of any length, and by using the general formula, we use the general formula in order to find out the area of the blue lens, and we use the same formula in order to find out the area of the big lens. We subtracted the two areas from each other, and we got the area of this orange shape. In the second method, we found directly the area of this blue lens, we found directly the area of this big lens, we subtracted the two areas from each other, and in this way we get the area of this orange shape that is equal to 9.77 square units. In both methods we arrive to the same result. Okay? So in the drawing, we have a square ABCD. One side of square ABCD equals to 10 units. Inside this square, we have two semicircles that intersect with each other and they create the blue lens. That is to say, the lens is the common area that belongs to both semicircles. Okay. In addition, we have in this drawing we have the quarter circle that intersects with this semicircle, and in this way they create the big lens. And our mission is to find out the area of this orange shape. It is very easy to see from the drawing that the area of the orange shape equals to the area of the big lens minus the area of the blue lens. Again, the area of the big lens minus the area of the blue lens will give us the area of this orange shape. So, in the first method, as I've already mentioned, we created a general formula to find out the area of any lens, and we put the data of the big lens inside the formula. In this way we found out the area of the big lens. Then we put the data of the blue lens inside the same formula and found out the area of the big lens, the area of the blue lens, and we subtracted the two areas from each other. In this way we found out the area of this orange shape. So here, then I explain to you two new concepts. What is the area of this sector, the green, in the green color, it is equal to the ratio between the angle between his legs, that is theta over 2 pi radians, so 360 degrees. The ratio between the two angles will give us the relative percentage that this sector occupies out of the whole circle, and when we multiply this percentage by the area of the whole circle, this will give us the area of this sector. Therefore, theta over 2 pi will give us the relative percentage that this sector occupies out of the area of the whole circle, and when we multiply it by the area of the circle, it will give us exactly the area of this sector. So theta over 2 pi times pi r square equals to the area of the green sector. Then I presented to you what is the area of circular segment AB. The area of circular segment AB equals to the area of sector AOB minus the area of triangle AOB. It is very easy to see from the drawing that if you subtract the area of triangle AOB from the area of sector AOB, we'll get exactly the area of circular segment AB. So the area of circular segment AB equals to the area of sector AOB minus the area of triangle AOB. Okay? Again, the area of sector AB, of circular segment AB equals to the area of sector AOB minus the area of triangle AOB. Okay? Then, I'll repeat again, that the area of the orange shape equals to the area of the big lens minus the area of the blue lens. Okay, the area of the orange shape equals to the area of the big lens minus the area of the blue lens. So here, as I already mentioned, in the first method, we created general formula that gives us the area of any lens, and then use the general formula for the area of any lens in order to find out the area of the blue lens, and then use the same formula in order to find out the area of the big lens. We subtracted the two areas from each other, and this gives us the area of this orange shape. Okay? So here, in order to create a formula for the area of any big lens, in order to create a formula for the area of any lens, here we have two semicircles that intersect with each other, and they create this lens. This lens is the common area that belongs to both semicircles. And because of the fact that the radius of this semicircle is A units and the radius of this semicircle is B units, therefore here we'll create a formula that is good for any lens. Okay, so this lens could be any lens. Why? Because the radii of the two semicircles are A and B. That could be, A and B could be any positive number. So in this way we create the general formula that is good for any lens. Okay, so here we have this lens, and we'll find out the area of the upper circular segment, and we will add e to the area of the lower circular segment, and this will be the area of this length that could be any length. So actually the area of the upper circular segment NL here, what is the area of this upper circular segment NL? It is very easy to see from the drawing that the area of sector MOL minus the area of triangle MOL will give us exactly the area of this circular segment ML. It is this area, the circular segment ML. Okay? And what is the area of circular segment ML? It is 2 theta, the angle between its legs, over 2 pi times pi r squared. But r equals to a, so it is a squared. In conclusion, the area of sector MON equals to theta a squared. Okay? Then we found out the area of the lower circular segment. The area of the lower circular segment equals to the area of sector NML minus the area of triangle NML. The angle between the legs of the sector MNL is theta pi minus 2 theta. Therefore, the area of sector NML equals to pi minus 2 theta over 2 pi times the area of the circle, that is pi r squared, but here r equals to b, so it is pi b squared. So the ratio between the two angles times the area of the circle equals to the area of this sector. So in conclusion, the area of sector MNL equals to pi b squared over theta minus theta b squared. And we also have to subtract the area of the triangle, so we will do it later. So in conclusion, we found out that the area of this length, that could be any length, equals to the area of the upper circular segment plus the area of the lower circular segment. Okay, the area of the upper circular segment equals to the area of sector MOL minus the area of triangle MOL, while the area of the lower circular segment of this length equals to the area of sector MNL minus the area of triangle MNL. In total, in conclusion, the area of this sector equals to the sum of the areas of the two sectors, this is equals to this expression, minus the sum of the areas of the two triangles. So in order to find out the sum of the areas of the two triangles, we combined the two triangles together and created quadrilateral MNOL with joint points N and O together by a straight line. In this way we created the two right triangles. We found out that the sum of the areas of those two right triangles equals to AB. So we subtracted AB, that is the sum of the areas of those two triangles, from the sum of the areas of the two sectors. In this way, we found out a general formula that is the area of this length that could be any length. Okay, so here the area of this length that could be any length equals to this expression. Then we took theta as a common factor. Inside the brackets we have a squared minus b squared plus this expression. Here we want to eliminate theta, so in triangle NOM, the right triangle NMO, we know the triangle theta equals to MN over MO. That is to say, it is equals to B over A. So tangent theta equals to B over A, therefore theta itself equals to tangent minus 1 of B over A. So Now we can substitute theta by tan exponents 1 over b over a. Okay, so we did it and we found out that the area of this length, that could be any length, equals to this expression. Now we can use this expression, that is the area of any length, in order to find out the area of the big lens. Then we'll find out the area of the blue lens. We'll subtract the two areas from each other, and this will give us the area of the orange shape that we are looking for. So first of all, we found out the area of the big lens. The area of the big lens was created by the intersection of the quarter circle with this semicircle. And we know that the radius of the quarter circle is equal to 10 units, that is to say a equals to 10, and the radius of the semicircle equals to 5 units. So we put the values of a and b inside this formula, and we found out that the area of the big lens equals to this expression. Then we use the same formula in order to find out the area of the blue lens. The area of the blue lens was created by the intersection of the two semicircles with each other, and we know that the radius of each semicircle is equal to 5 units, so a equals to b equals to 5. So we put the values of a and b inside this formula, and we found out that the area of the blue lens equals to this expression, 12.5 pi minus 25. We have already found out that the area of the big lens equals to this expression. Then we subtracted the area, so the area of the big lens, here, what is the area of the orange shape? The area of the orange shape equals to the area of the big lens minus the area of the blue lens. So here we have, this is the area of the big lens minus the area of the blue lens, gives us the area of the orange shape. So in conclusion, we found out that according to the first method, the area of the orange shape equals to the area of this orange shape equals to 9.77 square units. Okay. Then, in the second method, we actually found out directly the area of the big lens. Then we found out directly the area of the blue lens. We subtracted the two areas from each other, and this gave us the area of this blue orange shape. Okay, so now the area of the blue lens is created by the intersection of the two semicircles with each other. We know that the radii of the two semicircles, it is equal to 5 units, so a equals to b equals to 5 units. Now our mission is to find out the area of the blue lens. Okay, we found out the area of the blue lens by finding out the area of the upper circular segment, and we multiplied the area of the upper circular segment by 2, because those two parts are identical, they have the same areas, so we can multiply one part by 2, and this will give us the area of the whole blue lens. Okay, so here we actually So what we said, we found out the area of the upper circular segment, we multiplied by 2, and this gave us the area of the blue lens. Okay, so here, this is the upper circular segment of the blue lens. What is the area of the upper circular segment? It is very easy to see from the drawing that the area of sector MOL minus the area of triangle MOL gives us the area of circular segment ML. The area of circular segment ML equals to the area of sector MOL minus the area of triangle MOL. But because of the fact that sector MOL is a quarter circle, it means that the area of a quarter circle is the area of the circle over 4. The radius of this circle is 5. Therefore, the area of the circle is pi r squared, that is to say it is pi 5 squared. And then when we divide it by 4, we get the area of this sector MOL. Then we subtracted the area of sector MOL from the area. We subtracted the area of triangle MOL from the area of sector NOL, and we got the area of this circular segment. What is the area of triangle MON? It is a right triangle, therefore it is equal to the base of the triangle times the height of the base over 2. That is to say, it is equal to 5 times 5 over 2. Then we multiplied this area by 2, and this gave us the area of the blue lens. Okay, so in conclusion, the area of the blue lens equals to 12.5 pi minus 25 square units. Then we found out the area of the big lens. The big lens was created by intersection of the quarter circle with the semicircle. So first of all, we found out the area of this upper circular segment. The area of the upper circular segment equals to, of the big lens, equals to the area of sector NOL minus the area of triangle NOL. The area of sector NOL equals to, here, it is the 2 theta over 2 pi times pi 10 square, and the area of this triangle NOL equals to this expression. So in conclusion, we found out that the area of the upper circular segment equals to is equals to 100 times 10 minus 1 of 0.5 minus 40. Then we found out the area of the lower circular segment of the big lens. Actually, the area of the lower circular segment of the big lens, what is the area of the lower circular segment of the big lens? The area of the lower circular segment of the big lens will be equal to the area of sector NML minus the area of triangle NML. Here the area of the lower circular segment NL of the big lens equals to the area of sector NML minus the area of triangle NML. Okay? And in conclusion, we found out that the area of the lower circular segment NL equals to this expression, 12.5 pi minus 25 times minus 1 of 0.5 minus 10. Then we added the upper circular segment to the lower circular segment, and this gave us the area of the big lens. Again, the area of the upper circular segment of the big lens plus the area of the lower circular segment of the big lens equals to the area of the big lens. So we found out that the area of the big lens equals to 75 times 10 minus 1 of 0.5 minus 50 plus 12.5 pi. We have already found out that the area of the blue lens equals to 12.5 pi minus 25. And we know that the area of the big lens minus the area of the blue lens equals to the area of the orange shape. So here, I repeat again that the area of the orange shape equals to the area of the big lens minus the area of the blue lens. So this expression equals to the area of the big lens. This expression equals to the area of the blue lens. We subtracted the two areas from each other, and we got that the area of the orange shape equals to 9.77 square units. So here, in both methods, we arrive to the same result. We arrive to the result that the area of this orange shape equals to 9.77 square units. Okay, so I'll summarize again in two sentences what we done in this lecture. We actually found out the area of the orange shape that is equals to the area of the big lens minus the area of the blue lens. We found out the area of the orange shape in two different methods. In the first method, we created general formula for the area of any lens, and then we used this general formula in order to find out the area of the big lens. We used the same formula in order to find out the area of the big lens, and we subtracted the two areas from each other, and this gave us the area of this orange shape. While in the second method, we calculated directly the area of the blue shape, then we calculated directly the area of this orange shape, and we subtracted the two areas from each other, and the result is the area of this blue shape equals to 9.77 square units, and we actually arrived to the same result in both methods. I repeat again that the area of this orange shape that is equals to the area of the big lens minus the area of the blue lens equals to 9.77 square units. Okay? Thank you very much.